Now let's look at how to compute the confidence interval for our sample. We've already found the center of the interval, that is, the probability of a click. The equation was p hat, or the estimated probability, equals x over n, where x was the number of users who clicked, and n was the total number of users who visited the page. In this example, p hat is 100 over 1000, or 0.1, so the center of the confidence interval will be 0.1. Next, I want to calculate the width of the confidence interval, which is also called the margin of error, or m. To do this, I'll need to use the standard error of the binomial distribution. Recall that if the sample is large enough, instead of using the binomial distribution, I can assume the distribution is normal, like this blue line. A good rule of thumb is that if n times p hat is greater than 5, it's safe to assume a normal distribution. You should also check that n times 1 minus p hat is greater than 5, but for small click-through probabilities like we usually see, this is the more stringent condition. In our case, n times p hat is 100, so the assumption should be safe here. When we can use the normal approximation, then the width of the confidence interval, that is the margin of error, will be equal to the z-score of the confidence level times the standard error. And for the binomial distribution, the standard error is the square root of p hat times 1 minus p hat over n. If you look at this formula, you'll notice a few things. The amount of random variation we expect in our sample, the width of the confidence interval, is a function of both the proportion of successes and the size of the sample. This means we need to consider the proportion of successes when we decide how many samples to collect, which we'll talk about again later this lesson. When the success probability is farther from 0.5, then the standard error will be smaller, which means the distribution is tighter, which means the confidence interval will be smaller. Similarly, if the number of samples is larger, the standard error and the confidence interval will also be smaller. Now I'll need to find the z-score for the boundary of a 95% confidence interval. For a normal distribution with a mean of 0 and a standard deviation of 1, which is also called a z-distribution, with 95% confidence, the true value would be within 1.96 and negative 1.96 of the estimate we observed. The value 1.96 is called a z-score, and you can look it up in a table like the one linked in the instructor's notes. In this case, since we're doing a two-tailed test, each tail will contain 2.5% of the distribution. So 1.96 is the z-score for 97.5%, or 100 minus 2.5. In our case, the margin of error comes out to about 0.019. So we'll add this margin of error to the point estimate to get the upper bound of 0.119, and subtract to get the lower bound of 0.081. This means if you'd run the experiment again with another 1,000 page views, you'd maybe expect to see between 80 and 120 clicks, but more or less than that would be pretty surprising. Now let's say you made a similar measurement on a different page, and this time you got 2,000 total users, and 300 of them clicked. And let's say you wanted a 99% confidence level. Calculate the upper and lower bounds of the confidence interval, and write the numbers in these boxes to 3 decimal places. To do this, you'll need a z-score table, and you can find a link to one in the instructor's notes. Again, you should use a two-tailed test.